We're still working with systems of linear equations, but now
Toto, I have a feeling we're not in Kansas anymore.
we're not working with equalities, because life doesn't come that way for the most part. Things aren't equal. Get used to it. Okay, they're always a little bigger than you want them to be or a little smaller than you want them to be. So we're going to be working with systems of linear inequalities. Now, if something's not equal, it's either greater than or less than, right? Okay, and I'm going to ask you, of course, it's systems, to work with more than one at a time. Sometimes up to 5, maybe even 6 at a time. Before we do that, what we're going to do today is learn how, or hopefully review how, to work with just one at a time very well. And then at the end today, I'm going to look at just the kind of applications we'll get in business. We won't finish them off, but I'm going to give you a little bit of a flavor for that. Well,
let's play. Here we go.
let's try and solve one inequality. We're going to graph an inequality. Okay? Now, as soon as I said the word graph, I hope you know I always like you to, one way anyway, is to get y by itself. Well, let's see who's keeping y from being by itself. The 4x, which I'll subtract from both sides, and the 2 is right next to that y. He's multiplying, so I'll divide. Of course, I got to divide everybody. And I get y is greater than 4 minus 2x. Now, how am I going to draw a picture of this? All up to this point, I only know how to do equalities.
Welcome to Fantasy Island.
Well, you know what I'm going to do? I'm going to pretend that it is equal. It was greater, but I'm going to pretend it's equal. And then I know how to do it now. Remember, you make your chart, put in 3 points, put in 3 numbers. Put in the easiest 3. I'll put in 0. And let's see, 4 minus 2 times 0. 4 minus 0, I get 4. Okay, and I plot the point 0, 4. I put in one more. Let's put in 1 for x now. And apparently y would equal 2 in this case. 4 minus 2. And I'll plot that point over 1 and up 2. Let me put in, I always like to put in 3, just to make sure I didn't make a mistake.
What a maroon. What an ignoramus.
Put in easy numbers. You can put in anything you want, so put in easy. The easiest 3 I know are 0, 1, and 2. So if I put in 2, I'll get 4 minus 4, or 0. And if I plot that point over 2 and up none, I know, I'm very happy because I know they line up. Okay, that's what it would be if y equaled 4 minus 2x. I'd get that line. But remember, this is an inequality. Y doesn't equal 4 minus 2x. It's greater than 4 minus 2x. So here's how we're going to represent this. The line is where it equals. It's greater. If it includes the equals, like a greater than or equal or a less than or equal, then I will draw the line. But that's not the case here, is it? If it's just a greater and not equal, or just a less and not equal, I need to know where that line is, but I'm not going to draw it. So what I'm going to do, you may remember, is put a dotted line. Then, I got to represent all the points that are greater than that line, where y is greater. Where does y get greater? Above or below? Good thing you solved for y. Y is greater, so
Okay.
remember, you shade above. Okay. Now, you know we're going to have to do a whole lot of these at the same time, so let's look at a couple more examples.
Do that again.
In this example, I've got a less than or equal to. Still going to start off the same way, because I am going to graph, okay? I solve for y. I'm going to add 2x to both sides. And let's see, divide everybody by 3. Now, 3 divided by 3 is 1. And 2 divided by 3 doesn't go in evenly. So I simply write 1 plus 2 divided by 3. Or 2/3, we call it. Now, the reason I wanted to do this example is, of course, we're still going to pretend it's equals. I want you to think what you're going to put in. You can put in anything you want. We could put in 0, 1, and 2. We could do that. But it might make Might make life easier here if you put in multiples of 3, because it'll cancel out the fraction. So just consider that. Always try to make life easier for you. You'll have less errors. So I'm going to put in 0, 3, and negative 3. I could put 0, 3, and 6, but either one is fine. If I put in a 0, the second term will cancel, and I'll get a 1. And there's a nice point. Go over 0 and up 1. Okay, let's put in the 3. And you'll see that the 3's will cancel, and I'll get 1 plus 2, or 3. I happen to get out of 3. So I'll go over 3 and up 3. And I have another point. Now remember what I always tell you. Always do 3 points, because you could have made a mistake. So I'm going to put in another multiple of 3, negative 3. Now the 3's will cancel, but the negative won't. So I'll have negative 2, and I'll have to add 1 to that. And I get a negative 1. Remember how to graph that? Go back 3 and down 1.
Yeah, baby.
I can see they do in fact line up. Okay, now we've been in a fantasy world here with the equality. Remember how this problem began? It was a y is less than or equal to. And if it's or equal to, if it's greater than or equal to or less than or equal to, we're going to draw a solid line. If it's just greater than or less than, we don't want to include the line, so we do a dotted. But this time, I believe we do want to include the line, so we draw it. And then lastly, we have to decide to shade above or below. Once again here, it's good that we solved for y. Y is less. Where does y get less? It's either above or below.
Brilliance. That's all I can say. Sheer, unadulterated brilliance.
Really doesn't take a genius to figure this one out. Just go down. Okay, look down and shade below.
Thank you, sir. May I have another?
Let's do another one. Some of these get tricky. Okay, I'll give you a crazy one, for instance. In this one, oh, same thing. How are we going to begin? I said to graph. Okay, who's keeping y from being alone? Minus 3, and that's multiplying, so I'll do the opposite. I'll divide. Now remember, in these problems, these inequalities, when you divide
Wait a minute.
by a negative number, you're required to flip the sign. Maybe you forgot that. And that sign's important. So we'll flip it, and we'll get y is greater than 2. Okay, let's get 3 points. I'm going to pretend y is equal to 2, just like I did before. And I don't have any fractions here, so what am I going to put in? Don't make life easy for yourself. You don't have any fractions, don't need multiples of anything. Just put in 0, 1, and 2. Don't make it difficult. And this one's kind of so easy it's hard. If I put in a 0 for x, there isn't an x. If I put in a 0, well, it told me y is 2. So y is 2, dagnabbit. Over 0 and up 2. This one's, like I said, so easy it's hard. If I use 1 and I don't have any work to do, it says y is 2. Y is always 2 is the deal. Over 1 and up 2. And here's where you're glad you did 3 points. Because here again, y is going to be 2. And if I go over 2 and up 2, I'm betting
You look marvelous.
you feel a lot better about that because you can see they line up. The only trouble you have now is you have to decide, and it's not hard, is it solid or dotted? Well, it isn't or equal to, so I'm going to draw the solid or the dotted line. And y is greater, so we just shade above. And that's the answer. Okay? Let's do one very last inequality. How about this one? This is a little bit tricky. I want you to solve, but there isn't a y. Now you can sit here for a half hour if you want to. You can't solve for y because there isn't one. So we don't have too many options here. Do what you can. That's all you can do. Okay, so you're going to have to solve for x in this case. We're going to divide by 2. Note on this one that we're not going to flip the sign. We didn't divide by a negative. We didn't bring trouble to the problem. It was already there. So we're not going to flip the sign, and we'll have x is greater than -1. Now let's see. We're going to pretend x is equal to -1. I'm doing this example for a reason. What can I put in for x here? I said x is -1. Listen to me now. X is -1. What can I put in for x? -1. That's all you can put in. Okay? The neat thing is you get to pick any y. There's no restrictions on y. This is a little bit weird, isn't it? That's why I'm going over it. Well, if I get to pick, I'm going to pick 0, 1, and 2. That point -1, 0. Back 1 and up none. The point -1, 1. And the point -1, 2. Ah. Now all we have to decide first, is it solid or dotted? Now remember, this one's going to be dotted because it's not or equal to. Now this one you can't shade above or below, but remember we're not talking about y, we're talking about x. Where does x get greater, considering your only options are left and right? Well, x gets greater to the right, and that is your answer. Okay, and that's about as weird as it gets. Now some of these are not going to be easy to solve for y, and many of them are going to look like this. They're going to be in what we call standard form, where the right side is a constant. Remember that? Where we had the coefficients on the left side and the constant on the right. Some of them are going to look like that, and there is another method that I think is worthwhile for you to learn, and that's using intercepts. Remember that the y-intercept occurs when x is 0. 0 is easy to work with. And the x-intercept occurs when y is equal to 0. So those are two easy points. Maybe I could get those. I'm going to get the y-intercept by putting a 0 in for x. Nicely, the 0 term with the 2 will cancel out, and I'll be able to get y very easily. Dividing by 3, y will be 2, because I canceled. So put the y-intercept, 0, 2. I really only need one more point if you think about it, and that's going to be the x-intercept. Now the x-intercept occurs when y is 0. So I'll put a 0 in for y. Good old 0 is easy to work with. The term with the 0 will cancel out, and now all I have to do is divide by -2. You love 0. That'll cancel, and x in this case will be -3. So I have what we call the x-intercept, or the point -3, 0. And I know where the line is. I also know, in this case, that it's a solid line. The hard part, when I do it this way, is deciding do I shade above or below. Because I really haven't, you see, solved for y. Y gets bigger above and smaller below. The trick to this is to use, once again, use the 0 trick.
Now what am I gonna do?
I'm going to look at the point. I'm going to shade one of these sides. Look at the point 0, 0. I picked 0, 0 because it's easy to work with.
Here's someone who can help you.
The point 0, 0. I'm going to use it as what we call a test point. Of course, I'm going to put 0 in for x and 0 in for y. And what is that going to be? 3 times 0 minus 2 times 0. Every time it's going to be. Now, is this statement true? Is 0 less than or equal to 6? If it is true, then that blue point is part of the correct shading. If it isn't true, then that blue point is not part of the correct shading, and I should shade on the other side. In this case, 0 is less than or equal to 6, so the blue point is included in the correct shading, and that means it tells me which side to shade.
You are correct, sir.
I should shade the side below where the blue point is. And that's my answer. Okay, so use the point 0, 0, or any point. The reason I use 0, 0 is because it was easy to work with. Okay?
Show me the money!
Okay, what are we going to do? We're going to do some word problems here with this stuff. Now, I'm not going to finish off the problems because these ones require doing many inequalities at a time. I just want to set this one up, set a couple of them up. Okay, we should be good at this because we did this similar thing with equalities. Okay, what does this company sell? This company makes 2 models of personal music players. I think I know which company this is. The production costs for the standard model are $25 and $40 for the deluxe model. Now a store chain requests at least 100 of the standard model, and they want 75 of the deluxe model. Apparently they don't sell as many of the deluxe model. They sell the standard for $150, and they sell the deluxe for $250. If they must have a total revenue of at least $7,500 from the sales, that's what their goal is, how many of each should they make to minimize their costs? To minimize their costs. Wow. Well, we're going to start off the same way here. We have to name what our variables are. And in this case, it says how many of each type. Well, I think we have 2 types. So I'm going to let X be how many of the standard model of the music player, and Y be how many of the deluxe model. Okay, that was step 1. You have to name what your variables are. Now, if there was a super duper Barbie model or something, that would be Z, but we only have 2 models. Now, these type of problems are always going to have you maximizing something or minimizing something. And we'll have to come up with a function of what that something is. Well, in this case, they want us to minimize costs. So we're going to have to actually come up with, as confusing as it may seem, an equality function for costs. Now that's not that hard in this case, because the costs are given as $25 for each standard model and $40 for each deluxe model. So our cost function, in this case, cost is going to be 25 times X, the number of standard models we make, plus 40 times Y, the number of deluxe models we make. Okay, that's our cost function, and that's what there's always going to be, like I say, one function that we're going to minimize based on what we're going to call constraints. Now there's some constraints here. There's a constraint on what? On revenue. Okay, let's see. The store sells the standard for $150 and the deluxe for $250, and they have to have their revenue at least means equal or more than $7,500. Okay? So for each standard model, they get $150, and for each deluxe model, they get $250. Well, let's see. I think I want 150 times X plus 250 times Y to be bigger than, greater than, or equal to 7,500. Okay? At least means bigger than or equal to. Okay, any other constraints? The store chain requests that they have at least 100 standard models. Can't just sell all deluxe models or all standard models. They have to, well, they do have to have at least 100 and at least means more than. So I'm going to say X has to be more than or equal to 100. One other constraint. They request at least 75 deluxe models. So that means the number of deluxe has got to be more than, at least, equal to, or more than 75. I don't think we have any other constraints in this case. Notice we have one equation. One, we call it the objective function that we're going to maximize or minimize. In this case, we're going to minimize cost. Followed by several constraints to be met. And that's the type of thing that it's going to happen in all of these inequality problems. Now, if we do another example, I'm hoping you'll be able to see the similarities in what we do here, even though the problems will be quite different.
Played it for her, play it for me. Play it.
Okay, here's a very different type of problem. This is about running for office. We have a candidate that estimates that each 30-minute speech to a civic group will directly generate 15 votes. Now this is an estimate. Each hour talking on the phone generates 10 votes, and each hour spent shaking hands in malls generates 40 votes. We're talking about time here, hours spent. He wants to spend, we have some constraints here, he wants to spend at least twice as much time with civic groups as in malls, because he is civic-minded, that's why he's running. And he has to manage at least 5 hours on the phone each week. If he needs 1,000 votes to win, of course he can get more than 1,000, that's okay, but he needs at least 1,000 votes to win. How can he minimize his campaigning time each week to spend more family time? Wow. Well, let's not be overwhelmed by this. Let's first have the discipline to decide what our variables are. What's going to change in this? Okay, it's asking about time, but there are categories of time. There's time he spent in the malls, time he spent on the phone, etc. Okay, so let's start by letting x be the time, the number of hours he spent in the mall. Okay, and you could cross that out if you wanted. And the number of hours spent on the phone, and then what was the other one? The civic. Okay, now that was in 30-minute groups, but let's just call it hours for now. So Z will be the number of civic group hours. Okay? Okay, that's always going to be the way you begin. Name what your variables are, because you can't come up with any equations if you don't know what each of those variables are. And you're just guessing if you don't. And write it down. Now, another thing we're always going to have one function, one equation that we're going to try and maximize or minimize. Now, if you read at the end here, it's asking how can he minimize his campaigning time, the total campaigning time. How can he minimize his total campaigning time? So that's going to be a function of time, and it's the total of the three. So time equals x plus y plus z. In addition to our objective function, we're always going to have some constraints. Now let's see. This one's loaded with constraints. Let's talk about vote constraints. We got to get at least 1,000 votes. Now how are we going to get votes? We think we're going to get votes. Okay, based on how many hours we do in each of the categories. So for each, for instance, as it says here, for each 30-minute speech, I'm going to generate 15 votes at the civic center, at the civic group. For each hour talking on the phone, I'm going to get 10 votes. And for each hour shaking hands in the malls, I'm going to get 40 votes. And all that has to add up to at least 1,000. Remember that at least means greater than or equal to. Now this civic group thing, 30 minutes, if I work an hour, how many votes am I going to get? If I work half an hour, I'm going to get 15. So if I work an hour there, if I speak for an hour, I'm going to get 2 times 15, right? So that's why I hope you appreciate my constraint here is going to be 40x, 40 for every mall hour, plus 10y, 10 for every phone hour, plus 2 times the 15z. Okay? 2, since an hour has 2 30-minute periods. Okay? And all that is going to add up to hopefully more than or equal to 1,000, which is the number of votes. Okay? Any other constraints? Remember the 30-minute is half an hour. Okay? Well, let's see. He wants to spend at least twice as much time with civic groups as in the malls. The civic group is Z, and the mall group is X. So we want 2Z, remember at least then is greater than, 2Z to be more than or equal to X. So that's a constraint, and sometimes that's what they look like. Okay, any other constraints? At least 5 hours on the phone each week. Now the hours on the phone is Y, so that'll be Y is more than or equal to 5. Okay? So again, we'll always have one objective function that we're going to either maximize or minimize, and that's going to be, in this case, the time function. That's our objective function. And I'll show you how to do that next time. I just want you to be able to come up with the functions and the constraints. And so we have one objective function and then multiple constraints. There may be many of them. In this case, there's only 3. Okay, there's another example for you. Oh, now you have to come up with the work. So dig in, and we'll see you next time. Get that homework done.